this class. So we start with the definition of electrostatics. So let's see, what is electrostatics? Definition of electrostatics. Let's start with the definition of electrostatics. So what is electrostatics? Electrostatics is defined as a form of electricity that is stationary. A form of electricity that is stationary is referred to as what? Electrostatics. The form of electricity that is stationary, or you can say the form of electricity that is at rest. Alright? The form of electricity that is at rest is called what? Electrostatics. Please, give me your audience, don't get distracted. We said electrostatics is defined as a form of electricity that is at what? Rest, or that is what? Stationary. Are we following? If you observe, look at this word. Electrostatics. Electro means electricity. Statics means stationary, it is at what? Rest. So electrostatics, we said, is a form of electricity that is at what? Rest. Electrostatics can also be defined as the concentration of charges that are immobile. Electrostatics can also be defined as the concentration of charges that are immobile. The concentration of charges that are what? Immobile. That is an alternative definition for electrostatics. We said an alternative definition for electrostatics is what? The concentration of charges that are what? Immobile. Please take note. When electricity is at rest, it is referred to as a charge. When electricity is at rest, we refer to it as a charge. But when electricity is in motion, it is called current. When electricity is at rest, it is referred to as a what? Charge. But when the same electricity is in motion, when it is moving, when it is in motion, it is referred to as what? Current. In the study of electrostatics, the integral word is referred to as a charge. In our study of electrostatics, what you always hear us say is this word, charge. The unit of charge is the Coulomb. In the study of electrostatics, since electrostatics studies electricity at rest, and whenever electricity is at rest, it is called a what? Charge. It means all through the study of electrostatics, the most important word or the integral word you keep hearing is what? Charge. The unit of charge is what? Coulomb. The symbol is a capital C. The unit of charge is a Coulomb. There are two types of charges. Please listen up. I'm taking everything from the basis. There are two types of charges. Two types of charges. Number one is the positive charge. Number two is the negative charge. We said there are two types of charges. Number one is the positive charge. Number two is the negative what? Charge. We said two types of charges. Number one, positive charge. Number two, negative charge. The first man to discover stationary electricity is known as Coulomb. The first man to discover electrostatics, which is stationary electricity, is called who? Coulomb, a Greek scientist. As of the year 640 to 540 BC. That was when he discovered the form of electricity at rest. Thales was the first man to discover the form of electricity at rest known as electrostatics. He discovered stationary electricity by, listen up, he discovered stationary electricity by contact. He discovered stationary electricity by what? Contact. Now, how did he do that? He rubbed amber to a woolen cloth. When you rub amber to a woolen cloth, he observed that this amber became electrified. If you rub amber against a woolen cloth, the amber became electrified. He accidentally discovered this. Just like the way you take your pen cover, you rub it on your hair, and if you place it close to a piece of paper, it attracts the paper. Now what happens? That is charging a body by contact. Your pen is known as the uncharged body. Your hair is the charged body. So when you rub an uncharged body, when you rub an uncharged body against a charged body, that uncharged body absorbs electrons, alright, and it becomes what? Charged. But the word that was used by this guy failed. He said that when you rub amber against a woolen cloth, the same way you rub your pen on your hair, and that pen becomes charged or electrified. If you bring it close to a piece of paper, it attracts the paper. That was the same experiment Thales did. But he did that with amber. Now, what was amber? Amber is just a fossilized resin, a byproduct of a tree, the bark of a tree. When you rub amber against a woolen cloth, he observed that the amber became electrified, and that amber can attract piece of materials such as feathers. He was the first person to discover that you can charge a body by contact. A body can absorb electrons and become charged by contact. So the phenomenon of electrostatics was first observed by who? Thales. Although nobody's asking you this one in your test or your exams. Alright? But it's good you understand who discovered electrostatics. Where did it originate from? Alright? So Thales discovered electrostatics by rubbing amber against a woolen cloth, and he said amber became what? Electrified. The word he used was what? Electrified. It absorbed electrons. Are we following? Is there any question from this? Alright, so since we looked at the discovery of charges, the instrument that is used to detect charges is called an electroscope. An electroscope is the instrument used to detect charge, but the accurate instrument is called a gold-leaf electroscope. A gold-leaf electroscope is used to detect charges. The instrument that is used to detect this electric charge is an electroscope, but to be specific, it's called a gold-leaf what? Electroscope. The gold-leaf electroscope was discovered by Francis Hawkesby. Francis Hawkesby discovered the gold-leaf electroscope. Francis Hawkesby discovered the gold-leaf electroscope. I'm taking everything from the basis, so that when we get into the calculations, you won't have issues. If you understand everything I'm taking from the basis, when I get to electric intensity, electric potential, you fly. And the gold-leaf electroscope works on the principle of conservation of charge. The gold-leaf electroscope works on the principle of conservation of charge. The gold-leaf electroscope works on the principle of conservation of what? Charge. Now, what is the law of conservation of electric charge? The law of conservation of electric charge states that, please listen, the law of conservation of electric charge states that charges can neither be created nor what? Destroyed, but can be transformed from one form to a what? Another. That is the law of conservation of electric charges. And which instrument works on that law? Gold-leaf electroscope. Physics practical exam. Gold-leaf electroscope works on that, just like the way you wrote for first semester. Alright? So we said the instrument used to detect electric charge is the electroscope, and it works on the principle of conservation of what? Charges. Alright? Charges can neither be what? Created, nor what? Destroyed, but can be transformed from one form to what? Another. Alternatively, you can state the law of conservation of electric charge as the total or the net charge in a system is always equal to zero. The total or net charge in a system is always equal to what? Zero. It means no charge was lost in the whole transformative process of that system. That's another way of stating law of conservation of charge. The total or net charge in a system is always equal to what? Zero. Are we following? Are we following? We're following, right? Yes. We said there are two types of charges. Positive charge and what? Negative charge. Please take note. Charges emanate from the positive and terminate at the negative. This is where electrostatics begin. Electrostatics begins from this aspect. I said charges. Charges emanate from the positive and terminate at the negative. Charges emanate from the positive and terminate at the well, negative. It means the charges are always coming out from the positive and they are entering the well, negative. Let's see the resultant diagram of that particular statement. This is the positive and this is the negative. Alright? Charges, please listen up. Charges emanate from the positive and they terminate at the what? Negative. It means that, please listen up, your understanding of electrostatics begins here. It means that charges are always coming out of the positive terminal. What it means is that charges are always coming out from the positive like this. Look at the direction of this arrow. It's telling you that charges emanate, they come out from the positive and they enter where? Negative. It means they are entering negative. Look at the direction of the arrow. They emanate from the positive and they terminate at the where? Negative. Now look at this. Emanate from positive, emanate from positive, and they terminate at the negative. Now look at this. The direction of the arrow is what is important. Look at this. This is showing you that charges, electric charges, they emanate. It means they come out from the positive. They come out from the positive terminal and they enter the where? Negative terminal. Always emanate from positive and they terminate at the where? Negative. Please listen up. I want to explain some certain parameters here. Please listen up. This diagram, when you have two charges placed at a distance, please listen so you don't get confused. When you have two charges placed at a distance, when you have two different charges, positive and negative, placed at a distance, this is called an electric dipole. This diagram is referred to as an electric dipole. An electric dipole is when you have a positive and a negative charge placed at a small distance. When you have a positive and a negative charge placed at a small distance, what you've just created is called an electric dipole. There's something they call dipole moment. We'll get to learn that when we get to Gauss law. Alright? We'll get to learn that when we get to Gauss law. We said the whole of this diagram is referred to as what? An electric dipole. Please come here, listen up. When we say that charges emanate from positive and they terminate at negative, it means that there is a force of attraction between the positive and the negative what? Charge. These lines that you're seeing, it's just like, please take for example, if you have two bar magnets, you place them side by side, you see that they are trying to attract both of themselves, isn't it? It means there is a magnetic force in between them. The same thing will happen when you place a positive and a negative charge side by side. You are not seeing these electric lines of forces, but there is a force of attraction in between them. That force of attraction is called an electric force. And the field in between is called an electric field. So, whenever you have, this is attentively, whenever you have a positive and a negative charge held at a distance, what you successfully created is called an electric what? Field. In the presence of an electric field, there must be an electric force. When you have a positive and a negative charge placed side by side at a small distance, you've created an electric what? Field. The same way, when you have a magnet and a magnet placed side by side, you have a magnetic what? Field. That magnetic field produces what is called a magnetic what? Force. The same way, this electric field produces what is called an electric force. And that electric force is explained by Coulombs what? Law. Are we following? These lines you are seeing cannot be seen with the naked eyes. These lines are called electric field lines. Please take note. Electric field lines are lines that move from the positive to negative. You cannot see them with your naked eyes. What creates these electric field lines? When you have a positive and a negative, you'll find out that there are electric field lines to tell you that there is a force. See, observe. I have a positive, I have a negative charge. When you place a positive and a negative charge, alright, you have an attraction between the positive and the negative. For you to have a positive and a negative charge placed at a small distance, you have successfully created an electric field. And when there is an electric field, there is an electric what? Force. This electric lines of forces is just telling you that there is an electric field in between this positive and the negative what? Charge. Characteristics of electric lines of forces, or characteristics of electric field lines, whichever way. Characteristics of electric field lines. Characteristics of electric field lines. Number one, they do not intersect or cross each other. Characteristics of electric field lines. Number one, they do not intersect or cross each other. Number one, they do not intersect or cross each other. Number two, they move from the positive to the negative. Number two, they move from the positive to the negative. Number two, we said they move from the positive to the negative. Number three, characteristics of electric field lines. Number three, they are parallel to each other. Number three, they are parallel to each other. Number three, they are parallel to each other. Number four, the direction of the force, the direction of the force, the direction of the force, the direction of the force is tangential to the lines of forces. The direction of the force is tangential to the lines of forces. Those are four important characteristics of electric field lines. So we looked at four characteristics of electric field lines, isn't it? Number one, we said what? They move from positive to negative. Number two, they do not intersect or cross each other. Number three, they are parallel. And number four, the direction of the force is tangential to what? The lines of forces. If we understand, please listen, if we understand that whenever we place a positive and a negative charge side by side, we have successfully created what is called an electric field. This electric field produces what is called an electric force. If we understand to this point, please listen on. If we understand to this point, let's look at electric materials. There are three electric materials. Number one, conductor. Number two, insulator. Number three, semiconductor. This is an important aspect of exams. Number one, conductor. What is a conductor? A conductor, am I fast? I said there are three electric materials. Number one is a conductor. There are three electric materials. Number one is conductor. Number two, insulator. Number three, semiconductor. These are the three electric materials: conductor, insulator, semiconductor. What is a conductor? A conductor is any material that allows the movement of electrons, that allows the free movement of electrons. Any material that allows the free movement of electrons or electricity is referred to as a what? Conductor. Any material that allows the free movement of electrons or electricity is referred to as what? A conductor. Any material that allows the free movement of electrons or electricity is referred to as a what? Conductor. In your exam or text, wherever you see this question, whenever they ask you what is a conductor, the most important word is not that first definition I gave to you. The most important word is this. A conductor has its resistivity. A conductor has its resistivity as 1 times 10 raised to power minus 8 ohm meter. If you don't add this, what you said is trash. A conductor has its resistivity as 1 times 10 raised to power minus 8 ohm meter. Examples of conductor. Examples of conductor are SAC, SAC. Examples of conductor is SAC. What is S? Silver. What is A? Aluminium. Who can try? What is C? Copper. These are three important examples of conductor. They are materials that have resistivity as 1 times 10 raised to power minus 8 ohm meter. Next one is what? Insulators. Insulator or non-conductors. Please listen up. Insulators or non-conductors. They are materials that do not allow the flow of electrons or electricity. Materials that do not allow the flow of electrons or electricity. They do not allow at all. They do not allow the flow of electrons or electricity. They are called what? Insulators. They have resistivity. The resistivity of insulators is 1 times 10 raised to the power 4 ohm meter. Look at this. 1 times 10 raised to the power 4. The resistivity of insulator is a positive number. This is 1 times 10 to the power 4 is 10,000. 10,000 ohm meter. It means the resistance is very, very visible and big enough to impede any form of flow of current. The resistivity of insulators is 1 times 10 raised to the power 4 ohm meter. Examples of insulators are glass, paper, plastic, and wood. Examples of insulators are glass, paper, plastic, and what? Wood. Semiconductors. Semiconductors are materials that have resistivity in between conductors and insulators. Semiconductors, they are materials that have resistivity in between conductors and insulators. Please take note of this. Semiconductors are materials that have resistivity in between conductors and what? Insulators. The resistivity of semiconductors is 1 times 10 raised to the power minus 1 ohm meter. 1 times 10 raised to the power minus 1 ohm meter. If you're defining a conductor, insulator, or semiconductor, if you do not have their resistivity, your definition is not complete. Examples of semiconductors. Examples are carbon, silicon, isn't it? Arsenic, group 14 elements are all semiconductors. Germanium, etc. These are examples of semiconductors. Used to detect charge is called an electroscope. Which instrument is used to detect current? Nobody bothered to ask. To detect a charge is called what? Electroscope. The one that is used to detect current is called galvanometer. The instrument used to measure current is ammeter. The one used to detect current is galvanometer. But to detect electric charge is electroscope. Don't get confused now. The one with electrode is electric charge. Galvanometer used to detect current. Measure current is ammeter. Let's look at quantization of charges. Quantization of charges. Quantization means quantity of charge. When you hear the word quantization, we simply mean quantity of a what? Charge. To a physicist, quantization of a charge simply means that charges occur in integral amount. Quantization of charge simply means that charges occur in integral amount of the fundamental unit of E. That E is called a charge. Let's write that down. We said quantization of a charge, it means that charges occur in integral amount of the fundamental unit of charge, which is E. And the fundamental unit of charge is what? E. This is what we mean by quantization of charge. In simple terms, quantization of charge, let me explain it to like in a layman, so to a layman's understanding. You know that this E represents the charge, and one E or one charge is equal to 1.6 times 10 raised to the power minus 19 what? Coulomb. What does quantization of charge mean? Quantization of charge simply means that charges only exist in whole number. Look at quantization of charge means quantity of a charge. It means I can have 1 E. Charges exist in whole number. 1 E. I can have 2 E. I can have 100 E. Provided it's a whole number. I can have 1 million E. I can have 20E, I can have 200E, but I cannot have half E. You cannot have half E, you cannot have 3 over 2E. Charges do not exist as fractions, but they exist as what? Whole numbers. That is what we refer to as what? Quantization of charge. Quantity of a charge. Alright? Assigning a positive integer or a positive variable or a positive number to charge. Alright? Somebody might ask, is it only positive numbers? What about negative numbers? Yes, you can have a negative number, but provided it is not a what? Fraction. Assigning positive or negative numbers to charges is what we refer to as what? Quantization of charge. Alright? That is what we mean by quantization of charge. The formula for quantization of charge, quantization or quantity of charge, Q is equal to plus or minus NP. This is the formula for quantization of charge. Where N is a positive integer and E is 1.6 times 10 raised to the power minus 19 coulomb. And you know what is Q, isn't it? Q is what? Quantity of charge. Is anybody lost? Please, if you're lost, ask question. Yes. Can they occur in decimals? No. Decimal is something as fraction that you convert it. Charges do not occur. See, let me tell you. Charges do not, in quantization, please listen. Yeah, your question has reminded me something. Charges do not occur as fractions. Alright? But there are some charges that can exist as fractions, but they are rare. They are called test charge. Now, in Coulombs Law, please listen. Remember, I told you there are two types of charges, positive and what? Negative charge. In Coulombs Law, we have two types of charge. A point charge and a test charge. If you look at most questions in your textbooks, you always see this word point charge, you always see this word test charge. Now let's look at the difference. The question actually reminded me something. What's a point charge? A point charge is a charge. A point charge is a charge. Please listen up. A point charge is a charge whose magnitude or size is small compared to the distance of separation. A point charge is a charge whose magnitude is small compared to the distance of what? Separation. Point charges can be positive or negative. Please take down. A point charge can be positive or what? Negative. The charges used to describe Coulombs law are called point charges. Point charges cannot exist as fractions. In Coulombs law, the charge we are talking about is called a point what? Charge. Are you following? But in electric field intensity, electric potential, the charges we talk about there is called a test charge. Now, what's a test charge? Did you get the definition for a point charge? We said point charge is a charge whose magnitude is what? Small compared to the distance of what? Separation. And we said a point charge can be positive or what? Negative. Are we following? The next one is test charge. What's a test charge? Let's be fast. What's a test charge? A test charge is a point charge. Observe. A test charge is a what? Point charge. Are you seeing the difference? A point charge is a charge, but a test charge is a what? Point charge that is placed in the region of another charge. A test charge is a point charge that is placed in the region of another charge, and it is always positive. A test charge is a point charge that is placed in the region of another charge, and it is always what? Positive. Put it this way, or add to it, test charges are always located on the x-axis, the positive x-axis. Let me be specific. Test charge, you will take a question from the past question, you see them tell us that a positive test charge is placed 4 cm from the origin. When they say something is placed 4 cm from the origin, 4 cm from the origin to this aspect of the positive x-axis is where you have that test charge. Alright? So test charges are always what? Positive. And they are always located on the positive where? X-axis. Are we following? Alright, the law that governs electrostatics, is called Coulombs Law. The law that governs electrostatics is called Coulombs Law. Before we take Coulombs Law, let's look at the definition of a Coulomb. Before we take Coulombs Law, let's look at the definition of a Coulomb. We said the unit of a charge. The unit of a charge is called a what? Coulomb. And the symbol is capital letter C. Now, what is a Coulomb? Definition of a Coulomb. What is a Coulomb? A Coulomb is defined as the amount of charge. A Coulomb is defined as the amount of charge flowing through the cross-sectional area of a wire. You know, right? A Coulomb is defined as the amount of charge flowing through the cross-sectional area of a wire. A Coulomb is defined as the amount of charge flowing through the cross-sectional area of a wire in 1 second, in 1 second, not seconds, in 1 second, when the current passing through the wire is 1 ampere. I take it again. A Coulomb is defined as the amount of charge flowing through the cross-sectional area of a wire in 1 second when the current passing through the wire is 1 ampere. That is the definition of a Coulomb. And we said the law that governs electrostatics is called Coulombs Law. Coulombs Law and Newton's law of gravitation are known as inverse square laws. An example of an inverse square law is Coulombs Law, or you can say gravitational law. They are known as inverse square laws because they have an inverse square what? Relationship. So let's look at Coulombs Law. Coulombs Law. What does Coulombs Law state? Coulombs Law states that the magnitude of the force of attraction between 2 point charges, the magnitude of the force of attraction between 2 point charges, Coulombs Law states that the magnitude of the force of attraction between 2 point charges, hope you know what's a point charge. Hope you know what's a point charge. The magnitude of the force of attraction between 2 point charges, between 2 point charges, for you to have a force of attraction between 2 point charges, it means one charge must be what? Positive, and the other one will be what? Negative. Thank you. Are you observing? Because we said point charges can either be positive or what? Negative. In Coulombs Law, by using point charge, don't ever use test charge in explaining Coulombs Law or stating Coulombs Law. Alright? Let's proceed. Coulombs Law states that the magnitude of force of attraction, the magnitude of the force of attraction between 2 point charges, open a bracket, Q1, Q2. The magnitude of the force of attraction between 2 point charges, open a bracket, Q1, Q2, is directly proportional to the product of the charges, is directly proportional to the product of the charges, is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. And inversely proportional to the square of the distance between them. When you state Coulombs Law is talking about 2 point charges, isn't it? What Coulomb is saying is that if I have a point charge, call this Q1, and I have another point charge, call this Q2, separated by a distance, the distance from Q1 to Q2, this distance is what? R squared, isn't it? The proportional to the product of the charges, and inversely proportional to the square of the what? Distance. R is the distance, square of the distance separating Q1 and Q2. So, in between this positive and this negative point charges, there exists what is called an electric what? Thank you. But before that electric force, there is an information of an electric what? Field. So we have an electric force in between a positive and a negative what? Charge. So there is a force attracting it, there is a force of repulsion and there is a force of attraction. This electric force between these 2 point charges, Q1 and what? Q2. Hope you know that there are electric field lines. Like what we did, the electric what? Field lines. But what Coulomb is talking about is that between a point charge, Q1, and another point charge, Q2, separated at a distance, and we don't know the distance, alright? But the distance is always a square of that particular number. Coulomb is saying that the product of these charges, Q1 and Q2, is inversely proportional to the what? Square of the distance separating them. Whenever you state Coulombs Law, please give this resultant diagram or resultant explanation. So we can say that mathematically, it means that the electric force is directly proportional to what? Q1, Q2, and is inversely proportional to what? R square. You can say R1 to 4 square. Alright? This Fp is called electric force. This electric force. So if I introduce a constant K, if you introduce a constant, it changes this proportionality sign to what? Equality sign. So it means that electric force is equal to what? K Q1 Q what? 2 over what? R squared. Are we following? Yes. But please know we're not done. No? But K, this K is called proportionality constant. Don't get tired. This K is called proportionality what? Constant. This K is equal to 1 over 4 pi E naught. This K is equal to 1 over 4 pi E naught. What does this mean? It means that in place of this K, I will replace it with 1 over 4 pi E naught. And this is equal to Q squared over 4 pi E naught R squared. This is, listen, we can use this formula to calculate electric force. We can also use this formula to calculate electric force. But when do we use this and when do we use this? When you use this, whenever you use this particular K1, Q2 over R squared, whenever in your test or exam, they give you the value of this constant, K. If you don't see K in your constant, if I show you this test question, you see where they wrote constant. This college test question, there's no value of K. What they used was E naught. In this particular test question, look at it here. When I said there's no value for K. What they gave was what? E naught. So since they give you E naught, if they give you E naught and you use this one, it means you're bringing out your own formula. They gave you the value of E naught. So it means you're going to use U squared over what? 4 pi E naught R what? Squared. Because the only constant they gave for you is what? E naught. And what is E naught? E naught is called what? Permittivity of free space. Permittivity of free space. Let's find all the constants out here. So take a typical example. Alright, so why did I square them? I square them because Q1 and Q2 are point charges. Alright? Point charges, they have the same small magnitude. So since Q1 is equal to Q2, they are Q1 and Q2 are the same. They are like twins. They are the same exactly. So since Q1 and Q2 have the same magnitude, we can say Q1. Yes, you have a question. Any question? Since Q1 is equal to Q2, we can say Q1 and Q2 are the same. Alright, so we can represent them as Q because the both of them are point what? Charges. They have the same magnitude. So that is why I said you can see test charge. Two test charge do not have the same magnitude, but two or more point charge can have the same magnitude. That is why we said U1, this is point charge is what we use in Coulombs Law. So Q1 and Q2 are point charges. That's why I can represent, instead of writing Q1, Q2, I can just represent them with Q squared over 4 pi E naught R squared. So I said we have two formulas to calculate electric force. Formula 1, electric force is K Q squared over what? R squared. Isn't it? And the second formula, formula 2, this is Q squared over what? 4 pi E naught R squared. If you use this, you get the same answer. But for your test, when do you use this? Is when in your test they give you the value of this K. This K is a constant. K is a constant 8.99 times 10 raised to power 9 Newton meter squared per Coulomb squared. Whenever you see this constant in your test, you're using this particular formula. But whenever you see them give you something like this, giving that E naught is equal to 8.85 times 10 raised to power minus 12 Coulomb squared per Newton meter squared. Whenever you see them give you E naught, please take note. Whenever you see them give you E naught, you use this. If you use this or this, you get the same answer. But for being specific, when you use this particular one, K Q squared over R squared is whenever they give you the constant K. But if they do not give you the constant K, they give you the constant E naught, which is permittivity of free space. If you see this constant, you know that what you're using is Q squared over 4 pi E naught R squared. Please take note of this. Question 1. Let's take question 1. Only enough, this particular question, came out in test, college. The same question came out in exam, but they failed it. Do you know why? The same question, because look at the statement is compare the electrostatic and gravitational force of attraction. That's the question. We compare the electrostatic and gravitational force of attraction. But in the exam, people that did copy and paste, crammers rule, they now changed it in the exam. Compare the gravitational and electrostatic force. Test, they said compare electrostatic and gravitational force. When they say electrostatic and gravitational force, it means electrostatic over gravitational. But in exam, they now change it to compare gravitational and electrostatic. So those that cram, they now solve electrostatic and gravitational. So let's solve what is here. Compare the electrostatic and gravitational force. Let's take down the question. Compare the electrostatic and gravitational force between an electron and a proton. Compare the electrostatic and gravitational force. Compare the electrostatic and gravitational force of attraction between an electron and a proton. Assuming their distance of separation is 5.3 times 10 raised to the power minus 11 meter. Assuming their distance of separation is 5.3 times 10 raised to the power minus 11 meter. 5.3 times 10 raised to the power minus 11 meter. Given, they open a bracket, given, yes, distance 5.3 times 10 raised to the power minus 11 meter. 5.3 times 10 raised to the power minus 11 meter. That's distance. Given, now in a bracket, these are the given constants. Open a bracket. Mass of electron, Me. See how you write it? Mass of electron, M subscript E. Mass of electron, Me. Mass of electron, Me. Mass of electron, 9.1 times 10 raised to the power. 9.1 times 10 raised to the power minus 31 kilogram. 9.1 times 10 raised to the power minus 31 kilogram. Mass of proton, M subscript P, 1.7 times 10 raised to the power minus 27 kilogram. E, 1.6 times 10 raised to the power minus 19 Coulomb. And they said G, 6.67 times 10 raised to the power minus 11. And that's all. And they said K 8.99 times 10 raised to the power 9 Newton meters squared per Coulomb square. So these are the constants again. Solution, they said you should compare what? You should compare the electric to what? Gravitational force, isn't it? Good. So what I'm looking for is electric to what? Gravitational. If they say gravitational to electric, which one will be up? Energy will be up, isn't it? Good. So I know that electric force is Coulombs law. K Q what? 1, Q what? 2 over what? R squared. Fe is K1 Q2 over R squared, isn't it? This division line is this division sign. Are you seeing it? This division line is this division. What is Fg? Gravitational force. Gm what? 1 m2 over R squared. Isn't it? If you take reciprocal of this, it means the ratio of electric to gravitational force is equal to what? Kq1, Q what? 2 over what? R squared. If you take reciprocal, division changes to what? Multiplication. So that this becomes R squared over what? Gm what? 1, m what? 2. So this will take off this. But since the force of attraction is between an electron and a proton, and we change this Q1, Q2 to QE and QP. Hope you know what it means. Yes. QE, charge of what? Electron. QP, charge of what? Proton. So it means that the ratio of the force is K, QE, Q what? P over G, M, E, M, P. So we'll substitute. Alright, so let's substitute the value of K. The value of K. Let's substitute the value of K. So if we substitute, we have this to be equal to K is 8 points. And you think they gave us E naught, permittivity of free space. Am I going to use this one? No. I'm going to use Q squared over what? 4 pi. It means what I'll have here is going to be 4. You still get the same answer. Alright? Please don't forget. 8.99 times 10 raised to power 9. Make sure you put the unit. The unit of K, Newton meter squared and Coulomb squared, times charge of an electron. 1.6 times 10 raised to power minus 19. Times 1.6 times 10 raised to power minus 19 Coulomb. All over G, gravitational constant, 6.67 times 10 raised to power minus 11. You put the units, Newton meter square per kilogram squared, times mass of electron. Mass of electron from here is 9.1 times 10 raised to power minus 31 kilogram, times mass of proton from here 1.7 times 10, 1.7 times 10 raised to power minus 27 kilograms. So, whatever thing you get from here will be the ratio of the electric to gravitational force. It will not have a unit. It will not have a what? Unit. It won't have a unit because it's a ratio of 2 forces. There will be no units. Alright? There won't be any units. Anything you get is the answer if you're using passive effects. Okay? So that will be the answer. Are we following? Let's look at electric intensity. Let's just introduce electric intensity.